How do engineers actually decide what can go wrong in a vehicle? Before you can assign an ASIL, before you can define safety requirements, you first need to understand the risk. But what exactly does that mean in practice? How do you identify hazards? How do you evaluate situations? And how do you decide which risks are critical? This is exactly what HARA is about. In this video, I will explain hazard analysis and risk assessment in ISO 26262 and how engineers use it to identify and evaluate risks in automotive systems. Let's start with a simple question. What is HARA? Before engineers can define safety requirements, before they can assign an ASIL, they first need to understand the risk. But here's the challenge. In complex systems, risks are not always obvious. They depend on the system, the situation, and how everything interacts. So how do engineers make sure that no critical hazard is missed? This is exactly why HARA is so important. HARA provides a structured way to identify hazards, analyze situations, and evaluate risk. And without it, safety engineering would be based on assumptions instead of facts. So now that we understand why HARA is important, let's take a closer look at what it actually is. So what exactly is HARA? HARA stands for Hazard Analysis and Risk Assessment. It is one of the core activities in ISO 26262 and plays a key role in functional safety. The purpose of HARA is to systematically identify potential hazards in a system and to evaluate the associated risk based on real-world situations. In simple terms, HARA answers two fundamental questions. What can go wrong? And how critical is it? So, where does HARA fit into the overall ISO 26262 process? The results of this analysis form the basis for ASIL determination and the definition of safety goals. So where does HARA fit into the overall process? In ISO 26262, HARA is performed during the concept phase. It starts with the item definition, which describes the system and its boundaries. Based on this, engineers perform HARA to identify hazards and evaluate risks. The results of this analysis are then used to define safety goals and determine the ASIL. And this is important. HARA is not just another step in the process. It defines the foundation for everything that follows. If something is missed here, it can affect the entire development later on. So let's take a closer look at how engineers move from a system to a hazardous event. Let's now look at how engineers move from a system to a hazardous event. The starting point is always the item. This is the system that is being developed. Next, engineers identify potential hazards. A hazard is a potential source of harm caused by the system. But a hazard alone is not enough. We also need to consider the operational situation. This describes the context in which the system is used. For example, driving at high speed or driving in city traffic. When we combine a hazard with a specific operational situation, we get a hazardous event. And this is the key element that is evaluated in HARA. But there is one distinction that is often misunderstood. What exactly is the difference between a hazard and a hazardous event? One of the most important distinctions in HARA is the difference between a hazard and a hazardous event. A hazard is simply a potential source of harm. For example, unintended braking. But this alone does not describe the full situation. To properly evaluate risk, we need context. This is where the operational situation comes in. For example, driving at high speed on a highway. When we combine the hazard with a specific situation, we get a hazardous event. And this is what engineers actually evaluate in HARA. So here's a quick question. Do you think the same hazard can lead to different hazardous events? The answer is yes. And that's exactly why this distinction is so important. So let's take a closer look at operational situations and why they matter. Operational situations describe the context in which a system is used. This includes factors such as the driving environment, road conditions, and traffic scenarios. For example, driving in a city is very different from driving on a highway, and both are very different from driving in adverse conditions like heavy rain or fog. Now here's an important point. The same system can behave very differently depending on the situation, and this directly affects how critical a hazard becomes. So when engineers perform HARA, they must always consider the operational context. Otherwise, the risk assessment would not reflect reality. So once we have defined hazardous events and operational situations, the next step is to evaluate the risk. In HARA, risk is assessed for each hazardous event, and this is done using three parameters: severity, exposure, and controllability. These should already sound familiar. Each parameter is evaluated independently. Severity describes how serious the outcome could be. Exposure describes how often the situation occurs. And controllability describes whether the driver can avoid the situation. When these three are combined, they define the overall risk. And this is exactly what leads to ASIL determination. So let's take a closer look at how risk evaluation leads to ASIL. Now we can connect everything. Once the risk has been evaluated, the next step is to determine the ASIL level. The relationship is straightforward. Higher risk leads to a higher ASIL. Lower risk leads to a lower ASIL or even QM. But here is an important detail. This evaluation is not done for the entire system. It is done for each individual hazardous event. So every hazardous event gets its own ASIL classification. And this is what connects HARA with the rest of the development process. So once we have determined the ASIL, what happens next? Once HARA has been completed, the next step is to define safety goals. Safety goals are high-level safety objectives that address the identified risks. Each safety goal is derived from a specific hazardous event, and it is assigned an ASIL level based on the risk evaluation. In simple terms, safety goals describe what the system must achieve to remain safe. These goals then guide system design and the definition of technical requirements. So HARA does not just identify problems. It directly leads to concrete engineering actions. Let's look at a simple example to make this more concrete. Consider unintended braking. This is our hazard. Now let's define the situation. The vehicle is driving at high speed on a highway. If unintended braking occurs in this situation, the vehicle may decelerate unexpectedly. This creates a hazardous event. Now think about the consequences. At high speed, the severity is high because it can lead to a collision. And controllability is limited because the driver has very little time to react. So here's a question. Would you expect this to result in a high or low ASIL? In most cases, this would lead to a high ASIL classification. Now let's look at some common mistakes engineers make when performing HARA. Let's go through the most important ones. First, confusing hazards with hazardous events. A hazard alone is not enough to evaluate risk. Second, ignoring operational situations. Without context, the analysis does not reflect real-world conditions. Third, evaluating risk without properly defining the scenario. And another very common mistake, assigning ASIL too early. ASIL should only be determined after the full risk assessment. So the key is to follow a structured and complete approach. Let's summarize the key points. HARA is used to identify and evaluate risks in automotive systems. It starts by identifying hazards and defining operational situations. By combining both, engineers define hazardous events. These events are then evaluated using severity, exposure, and controllability. The results of this analysis lead to ASIL determination and the definition of safety goals. And this is why HARA is such a fundamental part of functional safety. If you want to go beyond this basic understanding of HARA, we provide a comprehensive ISO 26262 training course on our website. In this course, HARA and ASIL are explained step by step, including practical examples and how these methods are applied in real engineering projects. The focus is not only on understanding the concepts, but on applying them in a structured and effective way. You can find the link in the video description and also in the pinned comment below. If you found this video helpful, feel free to give it a like and subscribe to the channel. We regularly publish content on functional safety, ISO 26262, ASIL, ASPICE, and other engineering standards. Thank you for watching, and we look forward to seeing you in the next video.